Dear friends, today in lecture 2, I will cover the remaining topics in the unit electricity. I am planning to split this lecture into 2 videos so that the size of video will be less than 30 minutes. In the first video, I am planning to cover the revision of lecture 1 and the use of potentiometer for the calibration of ammeter. So, in the previous lecture, we covered the topics like use of Carry-Foster bridge for the measurements of resistance, resistivity, and the temperature coefficient resistance of the given resistance wire. And also, we covered the theory of potentiometer. And we learned that the measurement are done by comparing the given quantity with its standard value. And for that, we use an instrument to compare the given quantity with its standard value. That instrument is known as our measuring instrument. In electrical measurement, basically, we measure 3 fundamental quantities like current, voltage and power. But the measurements of resistance also very important in the case of design of electrical circuit. So, in order to measure the resistance, we can use the measurement of fundamental quantities like voltage and current, and dividing voltage by current gives the resistance. So, it didn't add it in the fundamental quantities. But if you measure the voltage and current and obtain the resistance, the value of resistance may not give the proper value. There will be more error in the reading. In order to reduce that error, we used some other methods. So one of the methods was using Carry-Foster bridge. So before the Carry-Foster bridge, we used Wheaton's bridge. Carry-Foster bridge is a modified version of the Wheaton's bridge. In the Wheaton's bridge, we used its balanced condition where we can easily find the unknown resistance. The methods that we discussed in the previous lecture. But there was some problem with this Wheaton's bridge. The Wheaton's bridge can't measure the small resistance because we have to get a standard resistance box which value is in the low range so that we can measure the low resistance. So we haven't have that low resistance standard box. So we have to think for another alternative method to measure the low resistance values. So in order to find the unknown low resistance value, we found that the modified Wheaton's bridge, that is Carry-Foster bridge, is a better instrument to measure it accurately. So we discussed about the design of Carry-Foster bridge, and using Carry-Foster bridge, we found that in the balanced condition of Carry-Foster bridge, we can easily find out the unknown resistance using our standard resistance box. And we found that unknown resistance X is always equal to R plus rho into L2 minus L1, where R is the resistance that we took in the standard resistance box in order to in our balancing condition, and rho is the resistance per unit length of 1 meter wire which we used in Carry-Foster bridge. So first we will find out the resistance per unit length of that wire using the same method like Carry-Foster bridge measurement method, where we use instead of unknown resistance, we use a strip of copper strip which makes the unknown resistance equal to 0, and in the side of the standard resistance we took 0.1 ohm. So using that we find out rho is equal to 0 rho, that rho is equal to, we got like R divided by L3 minus L4, where R is the resistance value which we took in the standard resistance. So instead of R, we can put 0.1 divided by L3 minus L4, where L3 is the balancing length we got when we put X in the left side of the Cayley-Foster bridge gap, left gap, and L4 is the resistance we got when we put that unknown resistance in the G4 gap, or right side the gap. And using that we found out the rho, and we can substitute that equation in the equation for unknown resistance, that is X equal to R plus rho into L2 minus L1, where L2 is the balancing length we got when we place that unknown resistance in the right gap, that is in the G4, and L1 is the balancing length we got when we placed that unknown resistance in the G1 gap. You just go back and see the lecture 1, then you will get more clear idea of that. I just want to brush up these things. Okay, and after that we found out the resistivity of that unknown resistance. We usually get unknown resistance in the form of a wire. So we found out the resistivity using the equation rho dash is equal to R into pi R square by L, where pi R square is the area, cross-sectional area of that wire, and L is the length of that wire. Okay, and then we find out the temperature coefficient resistance of that wire using our like two methods. One method was measuring the resistance at all the temperatures, from starting from 0 degrees Celsius, 10 degrees Celsius, 20 degrees Celsius, and going up to 100 degrees Celsius. And using the plot, we find out the temperature coefficient resistance using our equation, that alpha is the temperature coefficient resistance. Alpha is equal to 1 by R0 dr by dt, where R0 is the resistance at 0 degrees Celsius. Dr by dt we obtain from the graph. The graph was plotted by taking temperature along the x-axis and the resistance at a different temperature along the y-axis, and we took the slope of the curve that we obtained, by plotting the graph, and that slope gives the dr by dt. So we can find out the alpha from that graph, that alpha is equal to 1 by R0 dr by dt, where R0 was the y-intercept. That y-intercept will give you the resistance at 0 degrees Celsius. And we also find out the same coefficient, temperature coefficient resistance, using another relation. That relation was the equation for alpha, that equation for resistance at different temperature, using the equation for alpha, that is RT, the temperature at any temperature, so resistance at any temperature is equal to R0. Okay, you learned that if you want to get a temperature at resistance at a different temperature, we can use the relation like this change in resistance, that is RT minus R0 is proportional to R0, and RT minus R0 is also proportional to change in temperature, that is T. And if you take RT minus both in the equation, RT minus R0 is proportional to R0 into T, and if you put RT there, then it will become R0 plus R0. I think you are remembering that. That is, if you put equal to RT minus R0 is equal to alpha into R0 T. Okay, if you rearrange that, you will get RT is equal to R0 plus R0 alpha T. You can take R0 outside, that R0 into 1 plus alpha T. So we can write an equation, RT is equal to R0 into 1 plus alpha T. If you measure at two different temperature, then you will get at temperature T1, we can put at RT1 is equal to R0 into 1 plus alpha T1. Similarly, I can put RT2 is equal to R0 into 1 plus alpha T2. We can divide it and we can compare it, and we will get the equation for alpha from that equation also. So in two different ways we can find the temperature coefficient of resistance. Okay, that also we discussed in the previous lecture. And after that we studied the theory of the potentiometer, and from the theory of the potentiometer what we obtained is, if you want to get a potential difference of any device, what potential difference of any device we can measure using potentiometer. Okay, so if you want to get a potential drop or potential difference of any device, you can use potentiometer, and in potentiometer, if you can convert any electrical quantity into that DC potential difference, you can measure using that potentiometer. And we found that potential difference will be always proportional to the balancing length that we obtain from the potentiometer, or potential difference of the given source that given cell, that given battery that we took in the secondary circuit will be always proportional to the balancing length we get from the potentiometer, or that potential difference is equal to potential difference per unit length of the potentiometer wire into the balancing length. So potential difference of that cell that we balanced using potentiometer. Okay, we are taking that cell in the second arm or secondary circuit, and we will balance that potential against the potential drop in that wire, and that potential difference of that wire, when we can obtain using that balancing length, where we are getting null deflection in the galvanometer, that potential difference will be always equal to potential difference per unit length of that potentiometer wire into the balancing length what we got. So that was the potentiometer theory that we learned with them. Now in this section we will cover the remaining topics in the electrical measurement section. First, I am going to cover the calibration of ammeter. So what is the calibration? What is the process of calibration? In the calibration process, we check the accuracy of the result that we obtained from a measurement by comparing it with its standard value. So in the calibration, we check the correctness of that instrument, how correctly that instrument measures a quantity. So how we can measure it? So that is only possible, the correctness of that measurement instrument can be only checked by comparing its measurement with the reference standards. So using the potentiometer, using it as a reference standard, we can calibrate a ammeter. That means we can measure whether that, we can check whether that ammeter is giving the correct value of the current by using a potentiometer. So that's what we are doing. Actually what we are doing is we are checking the current that read by an ammeter is correct or not by measuring that current, or we are checking that current using a potentiometer. So how we can check that is learned in this section. So for that we need a circuit arrangement as shown in figure. You just see here. Okay, so what we are going to do, we are going to check the current measured by an ammeter is correct or not by comparing the same current which measured by ammeter. Okay, use that same current which the ammeter measures by doing a conversion in the potentiometer and checking whether these two values are same. If both the values are same, then the current measured by the ammeter is same. If there is any change, then we have to say that difference by saying that we can correct the measurement of ammeter. Okay. അപ്പോൾ നമ്മൾ ചെയ്യാൻ പോകുന്നത് എന്താണ്? നമ്മൾ ചെയ്യാൻ പോകുന്നത് അമീറ്റർ മെഷർ ചെയ്യുന്ന കറന്റ് അത് ശരിയാണോ? അതെങ്ങനെയാണ് നമ്മൾ ചെക്ക് ചെയ്യുന്നത്? നമ്മൾ ചെക്ക് ചെയ്യുന്നത് അതിനു വേണ്ടിയിട്ട് നമ്മൾ ഈ കറണ്ടിനെ പൊട്ടൻഷ്യൽ ഡിഫറൻസ് ആക്കി മാറ്റുകയും ആ പൊട്ടൻഷ്യൽ ഡിഫറൻസ് നമ്മൾ ഏത് വെച്ച് മെഷർ ചെയ്യും? നമ്മൾ പൊട്ടൻഷ്യോമീറ്റർ വെച്ച് മെഷർ ചെയ്യും. കാരണം പൊട്ടൻഷ്യോമീറ്റർ വെച്ച് നമുക്ക് എന്ത് മെഷർ ചെയ്യാൻ പറ്റില്ല? കറണ്ട് ഡയറക്റ്റ്ലി മെഷർ ചെയ്യാൻ പറ്റില്ല. നമുക്ക് എന്ത് മാത്രമേ മെഷർ ചെയ്യാൻ പറ്റുള്ളൂ? പൊട്ടൻഷ്യൽ ഡിഫറൻസ് മാത്രമേ മെഷർ ചെയ്യാൻ പറ്റുള്ളൂ. അങ്ങനെ മെഷർ ചെയ്തുകൊണ്ട് നമ്മൾ എന്ത് ചെയ്യും? ആ പൊട്ടൻഷ്യൽ ഡിഫറൻസും ഈ കറണ്ടിലോട്ട് കൺവേർട്ട് ചെയ്തിട്ട് ആ രണ്ട് കറണ്ടും സെയിം ആണെന്ന് നോക്കിക്കഴിഞ്ഞിട്ട് സെയിം ആണെന്ന് നോക്കും. അപ്പോൾ എന്തെങ്കിലും ഡിഫറൻസ് ഉണ്ടെങ്കിൽ എന്താണ് ഇതിന്റെ മെഷർമെന്റിൽ കറക്ഷൻസ് വരുന്നതാണ്. അങ്ങനെയാണ് നമ്മൾ എന്ത് ചെയ്യുക? ഒരു ഇൻസ്ട്രുമെന്റിനെ കാലിബ്രേറ്റ് ചെയ്യുക. So, usually calibrate in a content weighing machine calibrate and the standard quantity and standard quantity wages. That's correct. Difference adjust. അതേപോലെ തന്നെയാണ് നമ്മൾ ഇവിടെ എന്ത് ചെയ്യുന്നു ഡിഫറെന്റ് കറന്റ് വാല്യൂസ് മെഷർ ചെയ്യുന്നു അത് നമ്മളൊരു ഏറ്റവും സ്റ്റാൻഡേർഡ് ആയിട്ട് ഏറ്റവും കറക്റ്റ് ആയിട്ട് മെഷർ ചെയ്യാൻ പറ്റുന്ന വേറൊരു ഇൻസ്ട്രുമെന്റുമായിട്ട് നമ്മൾ മെഷർ ചെയ്ത് നോക്കുന്നു അത് രണ്ടും സെയിം ആണെന്ന് നോക്കുന്നു സെയിം അല്ലെങ്കിൽ നമ്മൾ എന്ത് ചെയ്യുന്നു ആ ഡിഫറൻസ് നമുക്ക് അതിന്റെ എറർ ആയിട്ട് കണ്ടെത്തണം സോ ഫോർ ദാറ്റ് വി ഡിഡ് ദിസ് കണക്ഷൻ സോ as in the previous case the primary connections are same this is our primary circuit in the primary circuit what we did the potentiometer wire okay these ends of the potentiometer wire are connected to two terminals of the cell this is for the biasing of that potentiometer and here one key will be there and in your circuit there will be a rheostat to adjust the current to this wire okay this is primary and this won't change in any case this will be the same and the secondary you see two circuits are there one is we have a standard cell okay you have to see that positive of this cell and the positive standard cell connected to common point A and from the negative we put connected to one another terminal we call it as 1 okay now you see the other section this is the section which this is the connection which we used to calibrate the ammeter here you can see that the ammeter is connected to a battery and from the positive of the battery it is connected to A okay and here also one resistance is there and one key is there another rheostat is there so this ammeter is connected in series with this cell resistance and a rheostat so rheostat is used to vary the current through this circuit and you can see that we are taking the potential drop across R to the circuit for that we connected a resistance here so in order to convert the current I to the potential drop we connected a resistance here so I think it's clear for you how the connections are made so this you can see this is our secondary circuit this completely our secondary circuit the secondary circuit we have a standard cell and we have a one more connection so in that connection the ammeter is connected in series with this cell resistance and a rheostat okay rheostat is for varying the current and this cell provides the current this cell will produce a current that current will go through this ammeter if you want to vary the current you can vary the rheostat and that will flow through that current will flow through the resistance so it will make a potential drop here this potential drop will given to our potentiometer to balance it against the potential drop across AB so here also this positive is connected to positive is connected to this A because all the positive should come here that you have to see and we are taking the potential drop across this R to this whatever current we are going through this that will make a potential drop here so we will see how the measurements or calibration is done I think you got the connection it's very easy connection it's very simple you see it and you think that the positive of this and positive of this should come here and the current whatever goes here that should drop across this drop should be given to the circuit so I taking it from here I am not taking entire thing I am taking from here okay and the third this is our usual circuit this won't change in any case there will be a galvanometer and there will be a high resistance box to protect this galvanometer and there will be a sliding contact or a jockey you see and now we will see how the experiment is performed we will start this we will put the key here so the current will flow through this and it will develop a potential difference across this wire so we can measure the potential difference per unit length of this by using our standard cell for that we are using this standard cell for that what we will do we will first connect the 1 to 3 then what we will do then the EMF of this standard cell is balanced against the potential drop across this AB for that we will move this jockey across this and we will get a balance in length So let L be the balancing length from A. For what? This I am doing for the standard cell. Standard cell is connected and we moved this jockey. We got a balancing point. There the galvanometer shown 0, 0. So we stopped there and we measured the length from A. That length I got as L. So we know that E, that is EMF of this S, is proportional to L. That is the theory of the potentiometer. Or what we know, that E is equal to potential difference per unit length of this wire into L, equal to, or I can write E by L is equal to potential difference per unit length of the potentiometer. So I am using this S to find out the potential difference per unit length of this wire AB. Okay, so what is the use of this standard cell? The standard cell I utilized to find out the potential difference per unit length of the potentiometer, which I can use it for the other case. Now we will see how we will do the measurement. So after finding out the potential difference per unit length of the potentiometer wire, I will connect 2 and 3. Okay, what I am doing? I am connecting this 2 and 3. And I will adjust the rheostat and here 2 and 3, and I will adjust the rheostat so that a current A0 or A1 is moving through this ammeter. So I adjust the rheostat to make ammeter reading A1. So I am getting reading of this ammeter as A1. Okay, so that current, whatever the current which producing the value A1 here, flowing through this circuit and flowing through the resistance, and it will produce a potential difference across this resistance. That potential difference will be balanced if I moved through this AB, if I move the jockey through this AB. So this is connected. That current which is flowing through A1 is producing a potential difference A1 into R here. Maybe it is different. Okay, because whatever it is reading may not be correct, so it will produce whatever current is flowing through this, that current is producing a potential difference across this. This measurement may be different, that A1 may be different, but the potential difference that is producing here is the current which is flowing through this. So that potential difference I will balance across this AB. So balance that PD across R, the potential difference across R potentiometer. Let L1 be the balancing length. Okay, so in this case we balanced that and we got L1 as the balancing length. So what I can write? Using the theory of the potentiometer, I can write PD across rho is equal to potential per unit length of the potentiometer into L1, and I got potential per unit length of the potentiometer as E by L from our standard cell. So current through R, this is potential difference across R. In order to get the current, what you have to do? You have to just divide it by R. So current through R is equal to EL1 divided by R by L. So what will be the correction if there is any change? This is the actual value. We know that potentiometer measures accurately. So this is the current through R. That current is also flowing through ammeter, but ammeter reading it is as A1, but actual current will be EL1 by RL. So correction the ammeter reading, how we will get? We will get the current that we can get from the potentiometer reading, that is EL1 divided by RL minus A1. Okay, this A1 is the reading of the ammeter. If the reading of the ammeter is correct, means this value will give us 0. If there is any difference, we will get that difference. Okay, usually what happens in the case of ammeter or voltmeter, in the low range case, the reading of the ammeter will be less, okay, or greater. Sometimes it finds out that sometimes it shows greater than the actual value. So we will get a negative value. But in the higher case, we will get the reading of ammeter's low value and the other one will be, actual value will be greater. So we will get a positive difference. So we can get negative difference as well as the positive difference. Negative difference is usually seen in the low range case. In the low range case, when you are measuring the low value of current like 0.1 or 0.2, what you will get instead of 0.1, ammeter may be reading 0.2, but actually maybe 0.1. So our difference will be negative 0.1. But when we go to 1.1 or 1.2 ampere reading, this will read as 1. But actual reading will be 1.1. So we may get 0.1 as positive. So correction may be positive or negative. Okay, it sometimes depends on that low range values also. So we can get the value, the actual value, by taking the difference. So following the similar procedure, we can also check the other ammeter reading. Now what I do, I can adjust the rheostat again. The ammeter will read A2. So the same procedure I can repeat. PD across R will be E by L into L2, because instead of L1 you will get L2. And you can get the current, that is EL2 by RL, that won't change. L you will change EL2. Then you will get the difference EL2 by RL minus A2. Similarly, you can go for A3, then L3 will come, A4. Like that, we can get the different, we can correct the ammeter reading for different values. And what we can do, we can draw a curve. That curve is known as calibration curve. The calibration curve for ammeter will take, along the x-axis we will take the ammeter reading, that is A1, A2, A3, and along the y-axis we will take the correction. Okay, delta A we will take, and we will get a plot. That won't be a straight line. That will be a different zigzag curve, maybe zigzag curve. So like that we used to correct the ammeter reading, and this is the way in which calibration of ammeter is done using a potentiometer. So I am stopping this video here, and the other topics will be covered in the second video.